Okay, 1927. This problem will go pretty quickly. We're given a wire carries a current of 10 amps in a direction that makes an angle of 30 degrees with the direction of a magnetic field strength 0.3 Tesla. Find the magnetic force on a 5-meter length of wire. So we just apply our magnetic force formula for this one. Not too bad. So we have B times I times L times sine of the angle in degrees, right? Well, yeah. Okay. And we just plug that in. And so 0.3 Tesla times 10 amps times 5 meters. Is that right? 5 meters and times sine of 30 degrees. So we have, this is all going to come out to a Newton. So we have 30 times 5 times sine 30 is 1/2. So that's equal to, we have 150. Oops. I made a mistake here. This is not 30. That should be 3. 3 times 5. 15 over 2 is equal to 7.5 newtons. That. And so what does it ask for? Find the magnetic force. So that's it. Okay, next problem, 1930. I've taken the time to draw this diagram. This indicates that we have a B field pointing into the page, right? We have a current moving along the wire in this direction. This is all given to us of length L. This is a square loop. Each side is length L. We have a resistor with resistance R, and we have an EMF over here. This is suspended in air, and it's hanging by a thread, insulated thread, a mass, right? The mass we're given is 1 kilogram. The B field is 2 Tesla, and the length is 0.5 meter. We are asked to find the current. What is the current along this wire? So, because this thing is suspended, because it's just kind of hanging out in the air, let's see if I have something, right? We need a force going upwards because this for sure is going to have a force pushing downwards. I mean, the wire is going to weigh something, the thread's probably going to weigh something, and the mass is going to weigh something. Even if we say these are negligible, right, which I think they do in the problem, this has a mass, and that means it has a weight force. This is going to need some magnetic force pushing upwards, right? And so we actually have a force law. Let's see, what was it? L I cross B. And if you don't recognize the cross product, it's L I B sine theta, which is something we actually have in the summary. And all we're saying is that we want to take the cross product of, let's say this current is moving here, take the cross product of this current with the B field here. So your right hand fingers point this direction and then point into the page. And that means that you're going to have, as I said before, a magnetic force pointing upwards. So all this really means is that we have an equilibrium. This is our magnetic force plus a weight force is equal to 0. Nothing is happening because we're just suspended in air, right? Okay, so now we have BIL sine theta minus mg is equal to 0. Okay, so now we have BIL sine theta equals mg. And we are trying to find the current. Well, guess what? We can solve for the current because that's what we have. So mg over B times L times sine theta. And because the force is perpendicular, because the current is perpendicular with the B field, sine theta is just 1, so it's mg over BL, which is going to be 1 kilogram times 9.8 meters per second squared over, B is 2 Tesla, and then L was half a meter. Well, these cancel. This leaves us with 9.8 amps, right? Okay, so that would be the current running through this wire, just using the force law that we have from the back of the book and setting it in equilibrium with the weight force. Okay, next we are asked to find the resistance given an EMF of 115 volts. So find R. Well, what we can do is use Kirchhoff's rules, right? We can't really use anything for the current. There are no junctions, but we can use around a loop, the sum of all potential differences must equal 0. Okay. I don't like that arrow. There we go. That's still not good. Meh. Okay, so let's look at this loop. Let's go. The current is going this direction, right? So now, as we go around this direction, we run into this EMF, negative to positive, right? That's going to put us at, positive. So we have a positive, and then we also have a negative value for potential at here because we're running along the direction of the current through the resistor, so that's negative, so it's negative I times R, and that's all equal to 0 because that's all we have. Sorry, I know I'm jumping around a lot. It's kind of hard to just go back and forth. So given that information, we have our EMF is equal to the current times the resistance. We're looking for this, right? So now we have EMF over I is equal to the resistance. That means that 115 volts over 9.8 amps is going to give us a value of around 0.85 ohms. That's the answer. Okay.